In this video we're going to talk about the chain rule, which involves composition of functions. So we're going to do a little review before we even start with the chain rule, and let's just remember how we write the composite function f on g. So this would just be applying g and then calculating f evaluated at g of x. So for example here, g is x squared minus 2x minus 1, so you could write it as f of, and instead of putting x, you put x squared minus 2x minus 1, and then you would obtain square root of 3, and instead of x, you have to plug in x squared minus 2x minus 1. And this types of functions we don't know yet how to calculate the derivatives of, but that is the content of the chain rule. That's what we're going to learn how to do in this video. So, but to actually calculate the chain rule, we need to identify the parts of a function. So for example, if you have the function h of x being square root of x squared minus 2x, let's find two simpler functions in that f and g such that h of x can be written as the composition of them. So for example, you could choose g of x to be the inside, and you could write it as x squared minus 2x, and you could choose f of x to simply be the square root of x. And you see that if you do f followed by following g, then you would have actually h. So this is the idea right here of what we need to do to calculate chain rule. If we needed to calculate the derivative of this expression, we would need to break it into two parts like this. Now, you'll say, well, that decomposition is not unique, and you'd be right. There are many ways in which we could write this function h as a composition of two functions, but this one will be particularly useful, or this is the one we want to look at whenever we're calculating the chain rule. So if you have a function, let me go back here. If you have a function h and you write it as a composition of functions, then the derivative, the chain rule tells you that the derivative is going to be derivative of f evaluated at g of x times the derivative of g. Let's calculate the derivatives here. As you can see, you will need f prime and you'll need g prime. So let's do a little example with this function. Let's calculate the derivatives of each one of them. So to calculate the derivative of g, that's an easy one. G prime of x is going to be the derivative of x squared, which is 2x, minus the derivative of 2x, which is 2. So that one is easy. Now the derivative of f, on the other hand, is going to be equal to, you can think about the square root of x as x to the 1/2. So you would lower the 1/2 and multiply times x to the exponent of 1/2 minus 1, which is negative 1/2. And that then is going to be, or you can rewrite it as 1 over 2 square root of x. And this is a very common function, so it's good to remember that derivative. All right, so in this case now, let's use the chain rule to calculate the derivative of h. And so here we can calculate h prime, and using the chain rule would be f prime evaluated at g of x. F prime is 1 over 2 square root, but now I don't evaluate it at x because it's not f prime of x, it's f prime of g of x. So I plug in, instead of x, g of x right here, which is this x squared minus 2x. Okay, that is the first part of chain rule, and then it says times g prime, and g prime is here 2x minus 2. Notice that you could simplify this expression by taking a common factor 2 up here and canceling with this 2, and that gives you an expression of the form x minus 1 over the square root of x squared minus 2x. So there you have it. You can calculate the derivative of an expression like h that we couldn't do before. There's no way we could have calculated this derivative before without using the chain rule. So let's do a few more examples to make sure that it all makes sense. So in this case, let's look at this one. We have a polynomial or binomial raised to the power of 7. So you could break this into two functions. Let's call them, sadly I already chose f, so let me call them h instead. Let's call h the outside function, so x to the 7th. And then g, let's keep it as the inside function, which is going to be 2x plus 3. So I always like to read this as derivative of the outside evaluated at the inside times the derivative of the inside. So let's calculate the derivatives. So h prime of x would be 7 x to the 6th, because it's going to be 7 minus 1. And then g prime is just 2. Okay. So now what do we do? Well, with the derivative of f now becomes h prime evaluated at g. H prime is going to be 7 times whatever you feed it to the 6th. But now I'm not feeding x, I'm feeding g of x, which is 2x plus 3. And then times g prime, which is 2. And that then gives me 14 2x plus 3 to the 6th. So there you have the derivative. Now imagine if you didn't have the chain rule, you would have to raise this or expand this polynomial to the 7th, and that will give you a degree 7 polynomial. It would take you a long time, but the derivative was actually pretty simple. So the chain rule is actually very useful. Let's do this one. We don't have to, I don't think we have to separate the parts anymore. You see how you have an outside function, which is going to be the function that raises x to the cube, and then the inside function will be the quadratic polynomial. So this would be derivative of the outside is 3, whatever you feed it, squared, and you want to copy the inside, so x squared minus 2x plus 7, barely fit it in there, times the derivative of the inside. So basically the derivative of the outside evaluated at the inside times the derivative of the inside, which is 2x, the inside being this function, 2x minus 2 plus the derivative of 7, which is 0. And that gives you there that gives you an expression. You could expand it or leave it just like that. You could also take a common factor 2 and multiply it in the front. It's completely up to you. I mean, you could do this 2 times and then have 6 x squared minus 2x plus 7 squared times x minus 1. So you could do that. Alright, so let's mix things up a little bit. For example, for this function, what do you have? Well, right here you have a quotient. So the way you want to look at this function is the following. So if I give you an x, what do? Well, you plug it in here, you multiply it times 5, you subtract 2, then you raise it to the power of 3, and then you perform this quotient. The last thing you're doing is a quotient, is a division. So that is the first thing you have to start taking the derivative of. It's always that way. You look at what you do last, and that's the first thing you start taking the derivative. So lastly, you would do a division, you do then the derivative of that, and that is a quotient rule. So you write it out. Derivative of the top, that's going to be 4 times the bottom, 5x minus 2 cubed. That's a cube. Let me rewrite it. It looks ugly. There. Minus, not that my handwriting is any good, but that was a little too bad. Minus derivative of the bottom. So let me add an extra parenthesis here because I'm just going to leave that derivative indicated. So write the bottom, and I'll leave the prime just to indicate I'm taking the derivative of the bottom times the top all over the bottom squared. Now the bottom squared, you have a cube, so when you square it, you multiply the exponents. Remember, that's one of the laws of exponents, and you obtain that 3 times 2 to the 6. Okay, so remember that. All right, so now we have to calculate this derivative right here. We can calculate it here on the side, and let me calculate it so we can do the derivative in full detail. So derivative with respect to x of 5x minus 2 cubed. So we do it separately. So the outside of, in this case, the outside function is a cube. So you will have to lower the 3. Then 3 minus 1 is 2. Copy the inside. And then you multiply times the derivative of the inside, which is just 5. So again, 3 multiplies, copy the inside, raise it to the power of 3 minus 1, which is 2. That's just doing a power rule. And then times the derivative of the inside, which is just 5. And that gives you then 15 times 5 minus x. Oh, sorry, 5x minus 2. Sorry about that. Squared. Which is multiplying the 3 and the 5 together. Okay, so with that, now we can continue with this derivative, and we're going to have 4 times 5x, that doesn't look like a 5, 5x minus 2 cubed minus, then I'm going to have this derivative, which is 15 times 5x minus 2 squared times 4x. So 15 times 4 is going to be 60, and then you're going to have x, and then you're going to have 5x minus 2 squared all over 5x minus 2 to the 6th power. Now, notice here that everyone has a 5x minus 2 to a certain power multiplied. So let's factor out and cancel. So let's take a common factor on the numerator, 5x minus 2, and the lowest or the smallest exponent is going to be a 2. So let's copy that 2 and let's factor out. The first term is going to give me a 4 times 5x minus 2. Why? Because I have 3 5x minus 2's, and I take out 2, I'm left with 1. And then minus, and here I'm going to take the 2, so I'm left with just a 60x. And then in the bottom, I'm going to have a 5x minus 2 to the power of 6. So let me scroll a little here. And notice now that this guy, I have 2 of them and 6 in the bottom. So you copy the 5x minus 2 in the bottom and raise it to the power of 6 minus 2. And that gives you a 4. So now you're going to have, you can distribute this 4 as well. It's going to be 20x minus 8 minus 60x all over 5x minus 2 to the power of 4. By the way, I should have canceled this whole thing out. Probably more clear. Okay, and now now that I have that, I can just operate this terms with x and then factor out an 8 out of that. So what I'm going to have is 20 minus 60 is negative 40. And minus 8 all over. Let's continue this so it doesn't look like the negative is outside. 5x minus 2 to the fourth. So you can factor if you want a negative 8, so negative 8 times 5x plus 1 all over 5x minus 2 to the power of 4. And there you have your derivative. Alright, I'll leave it at that because the video is already pretty long. So I hope it all makes sense. If you have any questions, please let me know in the comment section below. Alright, till next time.